Log Cosh Loss. Let us try to understand what are the specialities of log Cosh loss function and when to use this particular loss function. In the last few lectures, we learned about regression loss functions. This is also a regression loss function. We already learned about mean squared error. Then we learned about mean absolute error. Then we tried to find out what are the positives of mean squared error, what are the positives of mean absolute error, how to get both these positives and how to eliminate negatives on both sides. For this, we tried to come up with root mean squared error. Then we learned about Huber loss. Huber loss was a very good alternative which takes care of the positives of both sides and also makes sure that the negatives won't be affected. This time we are going to come up with log Cosh loss. So this is also having both the positives of mean absolute error and mean squared error. So this is a very smooth alternative to both. It is similar in characteristic to Huber loss, but there is some reason by which it is specifically useful over the Huber loss. So we are going to see what is specific with log Cosh loss. Okay. So let me erase these things off. First thing, what are we going to find out? It is a loss function. What is loss? Loss is the difference between what is the actual value, that is y, and the predicted value y cap. That is, if you have any input xy, where x is the input and y is the expected output. In that case, if you have a model and you feed x into the model, what happens? Your model will produce an output which is y cap. This is the value that is predicted by the model. This should have been same as y, but there will be some error because of which the prediction by the model might be a bit off from the actual expected output. So whatever is the difference between actual expected output and the value predicted by model, that is what you call as loss. We already discussed in previous lectures that you can't simply use this. Instead, you should have some particular mathematical formation that will be helpful for you in the upcoming calculations. That is, for finding out the gradient, in order to find out the loss, there are certain mathematical formulations required. So first of all, let me call this the residual value. From this, we have to find the loss function. It would be some sort of a representation of y minus y cap. This particular lecture is about log Cosh loss. So what is the loss function in case of log Cosh loss? Loss function will be log, as the name suggests, it will be log Cosh of your residual r. So this is the log Cosh function. One important thing here is, let us first understand y log, y Cosh, and what are these things. This is where we'll start this lecture from. Then we'll go deep into each of those parts. We should understand what logically is the significance in having these mathematical formulations. Then it is easier for you to understand it, and also when you get a situation to use it, it's easier for you to use it because you know why exactly this is required. This is the point. Okay. First of all, we'll clarify about Cosh. It is not cos, it is Cosh. What is the difference between cos and Cosh? The difference is cos that you generally know. This cos, it comes from trigonometry. It is trigonometric cosine. What is Cosh? Cosh function, this is hyperbolic cosine. This is the difference. So this comes from hyperbolic geometry, not from trigonometry. Okay, Cosh is not from trigonometry. It is coming from hyperbolic geometry, and it is not a periodic function like Cosh. One main importance you have to find out from the perspective of this particular lecture, if you just know this one thing, it will be good enough. That is the range of this function. The values that it will give you will be from 1 to infinity. Generally, cos function will give you from -1 to 1, right? But Cosh function is not this. Cosh function can take values from 1 to infinity, give values from 1 to infinity. I'll just draw the graph. the graph, if the graph of cos h is drawn, it will look something like this. If this is 0, then from here it will go upwards on both sides. So it will look like a smooth U curve. It is similar to a parabola, but it grows faster. Okay, this is the cos h function. So the main point you have to understand, it starts from 1 and it goes till infinity, and it is always positive. If you give negative values, then also the function is giving you positive value. If you give positive value, then also the function is giving you positive value. For now, just understand that the range is from 1 to infinity. This is good enough for you to understand this particular lecture. Okay. One more thing I'll clarify. The representation of cos h function, cos h of r, this can be represented as e power r plus e power minus r whole divided by 2. This is the hyperbolic cosine. Okay. So now let us get into the crux of the matter. Next question is, you understood why we are taking cos h, because we want to map it in this range of 1 to infinity. Next thing, why are you taking log? This is the next question. The use of log here is, because of the use of this log, it scales quadratically when it is near 0. So whenever you have this value near 0, it will scale quadratically, and then when it is exploded, that is when you reach larger errors, what was the main problem with your mean squared error? With mean squared error, the problem you had need not always be a problem, but you can call it a problem, that whenever the errors are large, they get magnified. So the error is already large. When it gets magnified by squaring, it becomes extremely large. This was the problem with mean squared error. In case of log cos h, the presence of log will help you to prevent it from exploding. So near 0, it will be quadratic, which means it will explode. And when it is larger error, automatically it will come to linear terms. This is where the use of log is used here. Okay, we'll see the mathematically how it is working. So first thing what I'll do is, I'll show you what happens with small residuals and large residuals. Okay, so residual is this particular value y minus y cap, error term. So in case of small residuals, that is, I'm explaining why this is a combination of MSE and MAE. Okay, this is the part I am clarifying here. For small residuals where R is nearly equal to 0, when the residuals are small, the value of cos h of R, this will be somewhat near to 1 plus R square by 2. If this is the case, then the value of log of cos h of r, the value of log cos h of r, this will be somewhat like r square by 2. So what happened here is, when your r is very small, if it is near to 0, when you take cos h, it will be 1 plus r square by 2. When you take log of cos h, it will be somewhat near r square by 2. That means your log cos h is functioning similar to mean squared error near r equal to 0. This is the first point. Next thing is, if your residual is very large, that is mod r, if this is a very high value, in that case what happens? Your cos h of r, this will function somewhat like half into e power mod r. And if cos h of r is half of e power mod r, then your log cos h of r, this will function like mod r minus log 2. In this case, this particular mod r is somewhat like the error term in mean absolute error. So whenever your residual is smaller, near to 0, log cos h function is functioning similar to mean squared error. Whenever your residual is larger, automatically your log cos h function is functioning similar to mean absolute error. Now one thing can be there in your mind. How is this value r square by 2? I actually directly wrote because for many people the actual solution may be insignificant. That is how I reached this r square by 2. But still, let's solve for one among these at least so that you understand how I read it here. Otherwise, it's like a black box, right? If I simply write r square by 2, you would also think how this came up. So let us solve this part. It may not be significant for everyone. So if you want to skip this part, you can just forward the video a little bit. I'll solve and show how the value of log cos h is r square by 2. Okay, so that you be clear about what we are doing, right? That will make your learning much easier. So what we'll do is, we'll start with this. What is cos h? Cos h of r, let us say cos h of r. If you want this particular value, I already showed you a mathematical formulation, but whenever you want to approximate around a particular point, you always use something called as Taylor series. Taylor series helps you to approximate these sort of mathematical functions. For example, here it is cos h. In the next lecture, we'll actually see what is Taylor series, how it helps and all. For now, just keep in mind there is something called Taylor series, which is used for approximating these sort of mathematical functions. Okay, so cos h of r, it can be written as, using Taylor series, we can write it as 1 plus r square by 2 factorial plus r power 4 by 4 factorial plus r power 6 by 6 factorial plus so and so. So this is an infinite series. Then you can ask, how are you approximating using infinite series? It depends on how closer you want to approximate. If you just take the first two terms, that gives you somewhat an approximation. If you take one more term, your approximation becomes even better. If you take one more term, it becomes even better, and so on. So this can be written as, I don't want to write all the terms specifically. Instead, I will write 1 plus r square by, what is 2 factorial? It is 2 only, plus r power 4 by, what is 4 factorial? It is 24, plus the remaining terms I'll simply write as order of r power 6. Okay. So the next step is, I have cos h now. I know how to express cos h. I'm now saying there is something called a. This a is cos h of r. A is cos h of r minus 1. This is the value of a. So if this is my cos h of r, what is cos h of r minus 1? So this one will go off. Then the term will be r square by 2 plus r power 4 by 24 plus order of r power 6, right? This is my a value, which is cos h of r minus 1. So from this particular value, I just removed 1 because I did a minus 1. Next thing I am going to do is, what if I take log? What do I actually have to find? I want to find log cos h of r. This is what I want to find. So what will be log cos h of r? I can also write this as log of 1 plus a. Because here a is cos h of r minus 1, which means I can write cos h of r as 1 plus a, right? So log cos h is log of 1 plus a. Next thing, there is a reason why I did this. I want it in the 1 plus a format. The reason is, again, I am going to use Taylor series. So if I have log 1 plus a, this function log 1 plus a, again using Taylor series, I can write it as log. So Taylor series we'll explain in the next lecture. For just now, understand that Taylor series defines a particular formulation for every mathematical function. Not every, for some particular functions. Okay. Log 1 plus a using Taylor series can be written as a minus a square by 2 plus a cube by 3 minus and so on. So this is the Taylor series expansion for log of 1 plus a. Next thing I am going to do is, you already know what is a from here. If a is this, this is the value of a, then what is the value of a square? If I want the value of a square, I'm just writing it here. Consider the value of a to be this, whatever we already derived. Then the value of a square will simply the square of those. So I'll just take the initial terms because all are not significant. First term is r square by 2. I'll take the whole square plus other terms are, we already know what order it is. So I'll simply put it as order of r power 6. Each particular term is not significant. So I can simply write this as r power 4 divided by 4 plus order of r power 6. This is the value of a square. Okay. I already know the value of a from here, and I know the value of a square from here. Why do I want the value of a and a square? Because I want to substitute those here. For log of 1 plus a, I am going to substitute those values. Let us see how I am substituting and how I am using those values. Okay. So given that I know the values of a and a square, how can I write those? So my value of log cos h, my value of log cos h of r, this will be, this we already discussed that log 1 plus a is log cos h of r. So I can write it as a minus a square by 2 plus like this. So instead of this, what am I going to do? I am going to say this is a minus a square by 2 plus, let us say, order of r power 6. So what does this come down to? I can write this as a's value I already know from here. So what will I write instead of a? I will write r square by 2. R square by 2. I'm just copying from here. Okay. Whatever I have written here, I'm copying the value of a. R square by 2 plus r power 4 by 24 plus order of r power 6. Right. So as of now, I'm not writing that r power 6 term. I'm just taking these two. Next thing is a square by 2 minus a square by 2. So in place of a square by 2, what will I write? I know a square from here. So I will write half of a square by 2. So a square is this, by 2 is half. Instead of a square, I'll write r power 4 by 4. And I'm keeping that order of r power 6 term there. Finally, I'll put order of r power 6. So the remaining terms are not so significant. That is why I'm putting order of r power 6. So if you further solve this, you can see r power 4 term is here as well as here. So if you join both, what happens? R raised to 4 by 24. Here it is r raised to 4 by 8. So this will become, this is 24, 8. If this is 24, 3 will be there. So instead, I am going to write this as, okay, I'll just show the combination here for you. R power 4 by 24 minus r power 4 by 2 into 4, that is 8. So this will come down to minus, let us say 1 by 12 r power 4. So if I do this, I can substitute this instead of these two terms. Then what happens? If I substitute this in this, I'm directly going to substitute. It will become r square by 2 minus r power 4 by 12 plus order of r power 6. So here you can see that the leading term here is r square by 2. So comparatively, the remaining terms will be even smaller. Here we are considering that the value of r is very small. That is, it is something near to 0. So r square by 2 is the leading term. The value contributed by remaining ones, which are r power 4 by 12 plus order of r power 6, that is very insignificant. Because of that, you can say leading term is r square by 2. That is how I wrote here log cos h of r is nearly r square by 2. That is why I put nearly equal to, not equal to, not actually equal to. It is almost r square by 2. That is what I wrote here. Okay. I just wanted to clarify this part so that you don't have the doubt of how I got that value. Now we'll get back to whatever we were talking about. Let me erase these things off. So I'll erase these calculations off, whatever we had done. We only want the actual values that we had initially written. Okay. All these things we don't want for the rest of our lecture. You understood those things, right? So this is our main part, the main calculation that we did. There are two cases. One is when r is nearly equal to 0, you have log cos h of r nearly equal to r square by 2. When r is a larger value, you have log cos h of r nearly equal to mod r minus log 2. So this is behaving somewhat like mean absolute error. This is behaving somewhat like mean squared error. Next thing is, in the previous loss function lectures also we had seen that we are always concerned about how or what happens when you take the derivative. So that is an important question here. Let us see what happens when we take derivative. Is it smooth or is there any problem? First of all, in first case, that is r is nearly equal to 0. In that case, if you do dl by dr, that is you are taking derivative with respect to r. If you take derivative with respect to r, what happens? It will be the function is cos h of r. So when you take derivative, it will be 1 by cos h of r, that is log cos h of r. So I'm first taking log cos h of r. So first will be log x is 1 by x. So it will be cos h of r into derivative of cos h. So derivative of cos h is sin h of r. So when you do this, you get tan h of r. So this is with respect to residual. If you take derivative, you get tan h of r. Next thing is, what you actually want is the derivative with respect to your prediction y cap. What happens then? dl by, if you take the derivative with respect to your prediction, then dl by dy cap with respect to your prediction, it will be dl by dr into dr by dy cap. This is the chain rule. So what is dr by dy cap? You already know that r is this. If you take derivative with respect to y cap, it will be minus 1 because this is having minus y cap. If you take derivative, it will become minus 1, which means this will be minus dl by dr. dl by dr is tan h, you already know. So this will be minus tan h of r. So what is your residual? R is y minus y cap. I am directly putting it here. Minus tan h of y minus y cap. This is the derivative that you got. What did you understand by this? First thing, it has this is the gradient derivative. The requirement is gradient because when you actually want to use this for optimization, when you use gradient descent, you should know what is the derivative. Derivative is going to guide you in deciding how much should you change your model parameters in each step. That is what is your aim. So here, when you got tan h as the derivative minus tan h of the residual as the derivative, what did you understand? First thing is, you have a bounded gradient because the value of tan h, this will be less than or equal to 1. That the mode of this value will be less than or equal to 1. So you can say this is a bounded gradient. Next thing is, this gradient, it saturates for large residuals. If the residual is large, it saturate means, that means you are robust against outliers. This is the main point. When you have points which are very far, let us say very far from the mean or median, then you are not going to explode your error. Instead, you will be robust against outliers. This is the most important point. Next thing, one important discussion is, we already discussed about Huber loss in the last lecture. So in the beginning of this lecture, we told that log Cosh loss is going to give you some sort of advantage over Huber loss. So what is that particular advantage? This is the most important question. So that important advantage is, Huber loss, we know it is piecewise because we use a particular threshold delta, and at that particular delta, suddenly the function changes. In log Cosh loss, you are not changing the function. You are always using log Cosh function itself. But because of the way log Cosh behaves, you are automatically getting a behavior which is similar to mean squared error in the beginning and similar to mean absolute error when the error is large. In case of Huber loss, you are putting a threshold and actually additionally putting effort in order to make it behave differently before that threshold and after that threshold. But in case of log Cosh loss, you don't have to put any threshold. You have the same function, same derivative. So it is smooth everywhere and it is not piecewise like Huber loss function. So this is the main advantage. So unlike Huber loss, you can say there is no sharp kink or there is no particular threshold value from where it directly changes. So where is this helpful? When you don't have a threshold, you are using the same smooth function. Where does it help you? It helps you in optimization. That is easier for gradient based methods. While you're finding the gradient, you don't have any particular points which are going to cause you concerns. So it is easier for you to use log Cosh loss for gradient descent. So the last point that we'll cover in our lecture is in which particular situations should you use log Cosh loss function? Why is this useful and where is this useful? So first thing, in regression tasks in machine learning, whenever you get regression tasks and those are the situations where you want a behavior such that when the error is small, you want it to be exploded, that is, you want it to be squared, and when the error is large, you don't want it to explode, you want it to be robust to outliers. In such cases, you can choose log Cosh loss. Next thing is, generally in many of the deep learning models also, log Cosh loss can be used. So if you want simplicity, you directly go for mean absolute error or mean squared error. If you want these characteristics to be handled, that is when you will go for log Cosh loss. So sometimes this log Cosh loss is preferred over Huber loss. The reason it is preferred is it avoids choosing one particular threshold which makes the function piecewise. So this is why log Cosh loss is important. In the coming lectures, we'll see about more loss functions and we'll see what are the specialities of all those.